Hello aspirants, welcome to OpSmart. So as in last class we have discussed about light rays, reflection, about concave mirrors and convex mirrors and various other cases of all mirrors. So today in this session we are going to discuss about the refraction, about the lenses and what are the applications of the lenses, what are the cases we will discuss here. Come on. The light. We have discussed about reflection. It is basically sends back the ray which falls on the surface. In refraction, it's a phenomena where the light passes from one medium to another medium and it changes the path while going from one medium to other medium. It changes the angle. Everything we will see here. Light refraction. Oblique passage is equal to direction change. So here when the light ray travels from one medium to another medium, obviously there will be change in direction and refraction causes speed change. So as the light ray passes from one medium to another medium, it changes the speed also depending on the medium from which it is coming and which it is moving to. Rarer to denser medium, denser to rarer medium. These are the two conditions. So, as you all know, air is the less denser medium and glass is more denser medium. Same here, air and glass, N1 and N2 it is there. Here, the light ray is coming from air, it is striking on the glass, then it moves inside the glass. The ray moves inside the glass. Always remember, when the normal is always drawn, when the ray passes from rarer to denser medium, it always bends towards the normal. It always bends towards the normal. It is passing from rare medium to dense medium. It will always bend towards normal. Normal kadege idu bend agutte. So when it passes from denser to rarer medium, it will move away from normal. Okay. So see, it moves away from normal. Here it bends towards normal. This is a basic application of the refraction. Like basic thing of the reflection, please always remember. Here the incident angle and refracted angle. Rarer to denser medium, reflected angle will be less than the incident angle. From denser to rarer medium, the incident angle will be more than the reflected angle. Always remember this. This is the basic concept. So we'll move next. Light refraction from air glass. Lateral displacement. It's the perpendicular distance by which the emergent ray is shifted from its original incident path. See, as there is shifting, right? It bends towards normal and this is the straight path which it might have traveled. So this distance is called the lateral displacement. See, the path which it has to follow and the path which it had bent and passing from same to the, see, I'll give you a brief information. This is glass, this is air, right? I'll take a blackboard. Assume this is glass, this is air, this is glass. When the ray is coming incident on the surface, let's draw the normal to it. It rarer medium, denser medium. It bends towards normal, right? The ray bends towards normal, R I. So then again, this is denser medium, denser to rarer again. It follows like this. Here it's also normal. This is emergent ray and this is incident ray I2, I1 emergent ray. So it might have followed this path initially, but there is some lateral dispersion. So this is called lateral inversion. This distance basically. So that is being explained here, lateral displacement. Then the angle of emergence that I have told you, the angle of emergence is this one. This one, the angle of emergence is this one. So next we'll see the effects of the refraction of light. What are the effects? Pencil partially appears bent. When we insert an object into the water, actually here this is the beaker, and here from this point we are seeing when we insert a pen, it should go like this, right? It should see like this in common medium, but here refraction takes place, so it looks like this. It changes the position. It should look like this, but it looks like it is bit lifted. We can see the apparent object. The pencil or the pen looks bit higher level than the original. There is slight bending in the frame. Then here the same is being seen. The fish, it looks apparent, the real depth of the fish is here, but it is seen bit above. This is the lateral displacement. It is any object inside the water, it looks bit higher when we see from the above surface. Atmospheric stars and twinkling. Atmospheric twinkling you have heard about, like the twinkling of stars. What it is basically means is that when we see stars, they are very far distance from us, as you all know. So as there is very large distance between them, the density of air changes from every level, stratosphere, thermosphere, in every level the density of air changes. As density of air changes, you can see ionosphere, mesosphere, stratosphere, thermosphere, density of the medium change. Actual position of the star should be here, but it looks somewhat here. This is apparently higher. That's different. As density changes, it looks here, but actual position is here. So for our eyes, it looks as it's twinkling. This is about that. Then we can see raised water level. You have seen the raised letter viewed through glass. It looks bit bulged. The lemon looks bit bulged. Then atmospheric layer, pre-twinkling, the same phenomena which I have told there is happened here. Then atmospheric refraction. 2 minutes early, 2 minutes delayed. Sun morning rises in the east and sets in the west, you all know that. But the thing is, 2 minutes early we can see the sun, and 2 minutes after the sunset we can see the sun. What's the real phenomena is that the sun is here, but when we are standing here, it looks the sun has a bit above, because here the actual position there is lateral displacement. This is lateral displacement which had a slight shift. As this is the earth, we are here and we are seeing the sun here, there is lateral shift. Sun is clearly visible before 2 minutes, and here after the sunset, sun is also again visible after 2 minutes from the same side. Same phenomena, there is lateral shift, lateral displacement. So sun is visible after and before the sunset and sunrise 2 minutes. This is about the atmospheric refraction. The next one, as I have said, like this already I have said, by drawing an incident ray passing through it, a rarer medium, denser medium, towards the normal. So this I is always greater than R, remember it. Then here the main concept arises is refractive index. Then there is loss of refraction. We'll get to know the refractive index. What is refractive index? Refractive index from n to 1. That is, this is n1. This is, sorry. This is n1 and this is n2. n1 is air, n2 is water. So refractive index is defined as like the density of air in n1 and density of air to n2, that is equal to sin I by sin R is equal to n2 by n1. It is defined as Snell's law, that is the incident ray, refracted ray and the normal ray lie in the same plane. See, the incident ray, normal ray, refracted ray all lie in same plane. They all lie in same plane, and the Snell's law defines the constant relationship of the sines. That is, sin I by the ratio of sine of incidence angle and the sine of refracted angle is always equal to the density of the second medium by the density of first medium. This is defined as the refractive index. See, they have given second medium with respect to first medium, n2 by n1. Always remember here n21, so n2 by n1. n1 to that is given as n1 by n2. Remember it. n21, so n2 by n1. Remember it. Then sine of angle of incidence and sine of angle of refraction is always constant. This is about the Snell's law. Then refractive index and speed of light. As I have said, refractive index is also written as n is equal to c by v. Refractive index I have told about Snell's law also, but the basic formula for refractive index n is equal to speed of light, that is equal to 3 into 10 to the power of 8 meter per second divided by speed of light in medium. We have to specify the medium, right? The formula, you should remember it. Next, they have given the refractive index of various other materials through which the light ray can pass through. See, diamond is having highest refractive index 2.42. Air is having a bit lower refractive index 1.0003. That is, air has very less denser medium, so obviously when the density of the material decreases, refractive index also decreases. When the density of the material increases, refractive index also increases. So density is directly proportional to the refractive index. Diamond is having a high density, so it's having high refractive index, that is 2.42. I think it is very necessary to remember the refractive index of the diamond and refractive index of the air as well as refractive index of the water. And crown glass, sometimes it is very important. Remember these refractive index values. So next we are coming to refraction of light by spherical lenses. We have seen spherical mirrors, concave and convex mirror. Same as here there is convex and concave mirror. Convex mirror, see, convex, x comes last, but it's inverse. Convex lens is like this. X comes at last, but convex lens is like this. Convex, x comes last, but it is opposite. It is the trick to remember. Concave, cave comes last, but it is like this, opposite. In lenses it is opposite. In mirrors it is the same. Here the basic thing, it's converging. Concave mirror, converging. Convex mirror, diverging. Here convex lens, converging. Concave lens, diverging. The basic thing that you should remember is you should imagine the lens. Concave lens. What is concave lens? It will be like this. Convex lens, x is at last, x like this, so it will be opposite. So convex lens is like this. You should always remember the figure, then you can guess it is converging or diverging. The rays are converging or they are diverging outwards. Right. Then here are some images given about the lenses. We can see them. Next, we are going to the principal focus and focal length of a convex lens. You have already seen the focal length, then the center of curvature from the mirror. So here it is not the center of curvature in the lens. Either we will use f focal length 1 and this is 2f dash or f1. This is f. This is 2f. F, 2f, f, 2f, f dash, 2f dash we will use. So in the convex lens, always the rays will converge and meet at the point of focus. Always in concave lens also, they'll converge and meet at focus. If the mirror is like this, they'll converge and meet at focus. As the same, here they'll converge and meet at focus. Every ray passing through the lens will meet at focus. So this is called the optic center. Then this is the principal axis. As you all know, focal length. The distance. This distance and this distance are equal. They are equal. Remember it. So next is the convex lens image formation, the key cases. I think I'll draw the images and which will be easy for you to remember, as I have drawn in the previous for mirror. I have drawn 6 cases, and it's now I'll draw for the lenses 6 cases. They are very important. Nature of the object and nature of the image, the enlargement or the size, and the position of the object and position of the image are very important. So please concentrate. All these 6 cases I'll draw and I'll show. So these are the concave lenses, convex lenses. So sorry. So all the 6 cases and another 2 cases in convex lens are very important. So go through it very efficiently to get a very good marks. So as you all know, the center point will be optic center. Then this is f dash, this is 2f dash, this is f, this is 2f. Same follows for everything. Same follows. I'm not gonna write for everything, but the same convention follows. They are equidistant, both the points. So we'll go through all the cases now. When the object is at infinity first case, so the object will be like this. It will be converged to the focus object. It will be converged. You'll have an a doubt that where actually the convergence takes place. It actually takes place at the center of the lens. The ray is like converged at the center of the lens, so it converges at the focus. Then the image is formed here. That will be a virtual array. Then the same here at 2f. It will converge, will pass a ray through the optic center. The image is formed between f and 2f. This is 2f dash, this is f dash. The second is so this is second condition. The image is not perfectly drawn there. I'll show you. Actually, at 2f2, we need perfect image for perfect angle to be drawn there. I'll draw it and show you there. See, when the object is at 2f dash, and this is f, this is 2f. See, the ray passing through here, it will go through the focus, then the optic center, so 2f2, when the object is at 2f2, image will be at 2f. Same size. So this is at 2f2. So beyond 2f dash, f dash, f and 2f. When it is beyond, through the focus one ray will pass, the another ray will pass through the optic center. Somewhere here, beyond 2f. When it is between f and c, the image is formed. This is at beyond 2f dash, when the object is beyond, object is at 2f dash at infinity. The next case we'll go through, that is between 2f dash and f dash. Here the object is at f and 2f. Here we'll place the object, one ray to the focal length and other ray so when the object is between 2f dash and f dash, the image will be formed beyond 2f. This is enlarged image, it is real inverted. Here it is also real inverted. Then this is f dash, it is f 2f dash, one ray passing through lens and one ray point through focus. And next other ray is going through optic center. So the points will meet at infinity. This is the image formed in this case. Next, between at focus is over. Here at f dash, the image formed at infinity. Then between f dash and o, here f 2f, one ray passing through this and another ray like this. They are actually very parallel. These two rays are very parallel. So image is formed somewhere here. In the last condition, image is formed somewhere here. This is virtual, erect and magnified. Remember, in the last condition of the convex lens, the image is enlarged, virtual and erect. So this is the condition for the concave lens. Rest these all lenses, the image is real, inverted and it is formed in front of the lens, when the other side of the lens. But in this condition, the image is formed in the same side of the object, same side, but it is enlarged than the object. So this is the image formed, and these are the 6 conditions which you should go through, and all the conditions are very important. Mainly go through the conditions in your imagine when we keep the image at a certain position behind the lens, what will be the image formed. This one condition will be like virtual, right? Leaving all the conditions, the image is formed real and inverted. So these are the conditions. We have gone through all the conditions. The same format is given here. Here they have given real inverted magnified image when between 2f dash and f dash. The same. You have perfectly learned the concave mirror. It's very easy for the convex lens to draw the figures or the ray diagrams. It's very easy for lenses also. Same positions, same magnification, same height of the image, same height will be in there for convex lens as same of concave mirror. So what are the uses of concave lens? Actually the same thing. All the 6 cases are given in class 10 NCERT science, physics first chapter, light ray. Go through that, all the 6 cases, it is given in a table. Go through that and easily you can map all the 6 cases easily. So uses of concave lenses. Vision correction. See, I'm using the lens right now. Vision correction, we can use the concave lens for myopia. Myopia is like short-sightedness. We can't see the images at the far position. So we use convex lens for myopia. That sign will be minus. Then Galilean telescopes for eyepiece system to see the far objects. Then multi-lens systems like this. There will be many lenses for optical instruments and cameras. The wide angle spy hole for door. As you have seen in many houses, there will be small hole. We can peek through it and we can see the outside objects in an enlarged way. For there it is being used. These are like bit applications of the concave lens. Then moving on, we will go to the lens convention formula, and the two cases of convex lens is concave lens. I will show you the two cases of concave lens. Only two cases are there, same like convex mirror. At infinity, at a finite distance. When the object is at infinity, same f dash, 2f dash, f, 2f. It will pass through focus. Another ray, it will also pass through focus. Here the image is formed, which is very minute, but it is virtual and direct image is formed. At a finite point, let's take the focus, then 2f, f, 2f dash. At a certain point, what happens is it will go through the focus and optic center, it forms somewhere here. Okay, but actually if we use scale and draw, a perfect image we can draw. In this case, what happens is a light ray, this is the focus, this is 2f, and this pass through this and this to pass through this. They are very parallel. They will not form there. They will form here somewhere. In second case, this is magnified, virtual, erect in same side of the object. Virtual erect and magnified image. Here virtual erect, highly diminished image is formed. These are the two cases at infinity, at a finite distance in concave lens. Remember these two conditions also. Next comes the sign convention. We have seen sign convention in the mirrors, concave mirror. Same sign convention follows here. Upside, when the object and image is towards up, it's positive. When downwards, it is negative. Towards left, it is negative. Towards right, it is positive. Upward positive, downward negative. Against the light, left side it is negative, it is given. Left to right, it is positive. The same rules for lenses, it applicable for mirrors, it applicable for lenses also. See, the formula is given here. 1 by f is equal to 1 by v minus 1 by u. And v you all know, it's the image distance. U is object distance from the lens. If this is the lens from the optic center, how much distance the object is there, and how much distance the image is there, or from this side how much distance the image is there. This defines the V and U. Remember it. This formula is important. Then obviously F, you all know focal length. This is focus and this is focal length. And then this is about the magnification. Magnification formula you already know for the mirror. M is equal to, for mirror I'll write first, H dash by H is equal to minus V by U. This is for mirror, right? So same here, nothing change. It is also H dash by H, image height by object height. But here in the lens what happens is, here the plus sign comes. Plus sign plus V by U, or V by U directly we can write. So in the lens, H dash by H is equal to V by U. Always remember this relation. They may give 3 and ask for any one value. So this is very important, and it's already given here. You can see it's already given here. You can easily remember. So next, moving on, we'll go to the power of the lens. What is the power of the lens? It's very important. Many of you are wearing, all are wearing specs. So what is the power of your lens? We will be always telling that minus something 1, minus 0.75 or minus 3. How will define the power of the lens? There is a formula for it, that is power is equal to 1 by focal length of that lens. Focal length of convex mirror, that is this. Focal length of concave mirror, that is this. Focal length of particular lens, not mirror, sorry, particular lens. This is measured in meters. Power is equal to 1 by focal length. You can easily remember. Like most of you, when have gone to eye test, you have seen like this. They'll show that is 1 diopter. It is like unit of lens power is defined in the reciprocal of in meters. The power of lens which is in 1 focal length, that is 1 diopter. So here you have seen simple conceptual, that is focal length of plane mirror is 0, so power is also 0. So here one concept arises, the power of combination of lenses. So what is the total power? Some will have astigmatism. Most will have the myopia and hypermetropia, minus and plus. Some will have astigmatism. So for them, what they'll do is they'll combine the both concave and convex lenses. So it's look like this combination of both the lenses. So the formula is P1 by P2, like just adding the power of this lens plus P1 plus P2. Power of both the lenses is added. That's it. Nothing more than it. Next, the last concept is the lens formula. You have already gone through the basic variations from the lens and the mirror. Lens formula we use minus in between. In mirror, here it is plus, and height ratio H dash by H, here also H dash by H, but here there is plus, but in mirror it is minus. Remember, in lens it is plus V by U, in mirror it is minus V by U. This, you have to remember this relation, mainly this relation, because it can be used in many applications. So for example, the height of the image or the distance of the image or distance of the object may be asked, you can easily find out by these formulas. So this is mainly about the lenses and the refraction part. You have to remember mainly refractive index, Snell's law. Then after that, the various values of the refractive materials you have to remember. After that, you have to remember about all 6 cases of the convex lens, and next 2 cases which I have drawn and shown for the concave lens. This is about the lens and the refraction part. So I think you have understood the most of the things. If there is any doubt, you can directly use all the AI and you can easily solve your doubts. This is about mainly the lens and the mirror. I hope you can also remember the mirror equations, like all the 6 cases of the concave and 2 cases of the convex mirror. So the table which is there is easily given in the class 10th NCERT physics first chapter, that is light. So you can visit class 10th NCERT for more descriptive things. So this is about the ray light chapter. So thank you.